ME204, relative motion. Here's an example of relative motion and what we're going to discuss today. Imagine that these two jets are in outer space. They're spaceships in the blackness of space. They're traveling at a constant speed, and we've discussed before that if you're traveling at a constant speed, you can't tell that you're moving. So both of these spaceships would think that they were standing still. And if they looked out of their cockpit at the other spaceship, they might think that the other spaceship was traveling directly toward them on a collision course. So they might call each other on their radio and say, "Hey Bob, you're an idiot. You're coming straight toward me. I'm just sitting here not moving at all and you're moving directly toward me." Well, the other spaceship would reply in the radio, "No, you're the idiot. You're the one coming directly toward me." So that's what we're analyzing today, is the motion as perceived by a certain person on a certain reference frame. Your mind already knows how to calculate this relative motion, and I'll prove that you know the equation. The main equation for relative motion, your mind already knows it, and I'm just going to prove that you already know it. Remember this nostalgia of the good old days, riding on a school bus? Does that bring back great memories, looking down the aisle of the school bus? Well, let's say that this bus is traveling 55 miles an hour and there's a goof-off on the bus that gets up and starts running down the aisle at 5 miles an hour. How fast is that boy really moving? Well, if you said 60 miles an hour, you're right, and your mind just computed the relative motion equation. You just derived it in your own mind. So let's write an equation for your mind just did intuitively. In order to write an equation, let's put some subscripts on things. We'll call the bus driver's name Alvin, and we'll call the boy B for boy. So if we wanted to know the actual velocity of the boy, we took the actual velocity of Alvin and added to it the boy's relative velocity, the boy's velocity relative to the bus. We could rearrange it to look like this and find out what's the relative velocity. In other words, if we knew that the boy was truly moving at 60 and the bus was only moving at 55, well then the boy must have been running down the aisleway at 5 miles an hour. So it's important to realize that the boy is running at 5 miles an hour, but that's only relative to the surface that he's running on. Here's another example. Maybe you prefer to think about it this way. Maybe the example of the school bus doesn't bring back such nostalgic feelings for you. Here's a good example. I've been to the airport and my kids have goofed off on airport walkways before. So let's say there's a walkway. The walkway is moving at 5 feet per second. And this is maybe my 11-year-old son walking 5 feet per second backwards on the walkway. How fast is my son actually moving? He's not moving at all. It's like he's walking on a treadmill. So let's write an equation for what your mind did intuitively. Well, let's call the walkway A and my son B. We wanted to know the actual velocity of B. We added the A with the relative portion, B with respect to A, and we noticed that that is his relative velocity. The 5 feet per second is only relative to the surface he's walking on. And of course it's in the negative direction in this case. Okay, so the velocity of B relative to an observer at A is defined as, think of the boy on the school bus, and I bet you could derive this in your mind, so pause this video and think of the boy on the school bus, or my son on the airport walkway. Did you say B minus A? If you did, you're correct. Since vector addition forms a triangle, there can be at most how many unknowns? There's a triangle. If we knew a 90 degree, there's one known, and I knew two other sides, there were two other knowns, then I could find that side, I could find this angle, and I could find that angle. So at most, I could only find 3 unknowns in a triangle. Let's look at relative position. Sometimes we want to know how far something is away from a certain observer. Let's take these two observers. Observer at O is fixed. This person at A is moving along the path shown there in the blue. And we want to find the position of object B relative to A. If position A and B are known. Well, we have the position of A relative to the observer at O, who's fixed. We also have, and we could write that as a vector. It could be a 5 and a 4. We could write the position of B as a vector, a 10 and a 2. Then we could say, well, the position of B relative to A would be this vector. And we could use this Bubba equation. We call it the Bubba equation. Remember this? That's what we just discovered when we were talking about the boy on the bus, or my son on the airport walkway. So if we want to know B, the relative position B with respect to A, we could rearrange that equation and take vector B, subtract vector A, and we'd get the relative vector of B with respect to A. So let's do that. We're going to take the B vector minus the A vector, and it shows us that it's a 6i and a negative 3j. Let's see if that's true. Sure enough, I go 6 in the I, and I go negative 3 in the j. So that's correct. The vector math worked. Relative velocity and acceleration are similar. The Bubba equation works for those as well. If I want to find the actual position at B, I take the vector sum of the actual at A and the relative of B with respect to A. Velocity is the same way, and acceleration is the same way. We call that the Bubba equation. Here's an example. The water in the river is flowing at 2 feet per second. If the person aims his body straight across the river in that y direction, how fast would he have to swim in order to arrive at the opposite bank just before going over the waterfall? Well, let's find out how fast this person is actually moving. We know that the river is moving only in the I direction and not the j direction, 2 feet per second in the I direction. We know that the man, with respect to the river, is only going in the j direction. The problem stated that he's aiming directly across the river. So as he swims in the river, he's swimming only in the j direction and at some unknown speed. So we know that the total velocity has an I component caused by the drifting of the river and a j component caused by the person swimming directly across. So there would be this person's velocity as two components of a vector, and there is his actual velocity that we're finding right now. So in the x direction, how long will it take him to drift 30 feet downstream? Well, in that x direction he's moving 2 feet per second. So the distance is 30 feet and he's going at 2 feet per second, so it takes 15 seconds to drift that 30 feet downstream. How fast does he have to swim to go 40 feet in 15 seconds? Well, 40 feet divided by 15 seconds means he has to swim at 2.7 feet per second. So since these relative motion equations are vector equations, problems involving them may be solved in one of two ways. First of all, we could do the vector math that we've been doing up till now, using this Bubba equation. But because they're vectors, we could also do it graphically. We could use the law of sines or the law of cosines to figure out unknown sides of a triangle. I'm going to also introduce method number 3, which a textbook would probably never introduce, but is probably the most common in industry. I call this, we do using the graphical method, but rather than using trigonometry, we actually just draw the vectors in a CAD system and measure the resultant vector. And we didn't have to do any math at all. We just draw it to the right size, measure the unknown. So let's review the law of sines and cosines. Since vector addition or subtraction forms a triangle, sine and cosine laws can be applied to solve for relative or absolute velocities and accelerations. So here's a review of those formulas. Here's the law of sines. Side A divided by the length of side A divided by the sine of angle A is the same as the ratio of B divided by sine B, which is the same as the ratio of C divided by sine C. Here's the law of cosines. Hopefully those are not foreign to you. Brush up on those. Let's work another example. Here's two airplanes. One is going 60 kilometers an hour, airplane A. Airplane B, 700 kilometers an hour. Let's find the rate at which they are approaching one another. That's velocity B relative to A. In other words, if you're the pilot in plane A and you look out your cockpit, it appears that airplane B is approaching you at what speed? Let's find that out. So we're going to do this problem using both method 1 and method 2. Method 1, we're going to do it using vectors and vector math. Number 2, we're going to do this the graphical method and use the law of sines and cosines. Okay, so here's the vector math method. Well, velocity A, we could break that into its components, I and j components. There's some decimal numbers. Velocity B, we could break that into its I and j components. And we know that B relative to A would be the difference between B and A. And so the velocity that B approaches A is the square root of sum of the squares. That would be the magnitude. So it appears, if you're the pilot in plane A, it appears that that plane B is approaching at 1,240 kilometers an hour. And we could also find the angle using an inverse tangent. Okay, now let's do the graphical method. We take two vectors, put them end to end, tail to tail, velocity B and velocity A, and the difference between those vectors would be the red vector that's shown, and we can use the law of cosines to figure out that length, because we would know that angle. We could also use the law of sines to find the unknown angle there in the red. So I want you now to answer these questions without doing any math. There are two particles, A and B. They're moving in directions shown. What should be the angle so that the relative velocity is as small as possible? Well, if that one was going directly this way, they would only be separating by 1 foot per second. If they were going this way, they'd be separating much quicker. And if B was going this direction, it would really be separating quickly. So certainly, if B is going in the same direction as A, then they won't be separating very quickly at all. Here's question number 2. We've done this one before, but let's see if we could do this graphically without doing any math. Determine the velocity of plane A with respect to plane B. In other words, if you are there at that blue dot on B, what does it look like A is doing? Well, it would look like A is traveling straight at you. So that vector is a positive x direction and a negative y direction. So let's look at the answers. Which is a positive x and a negative y? That's the only option. So we didn't have to do a single bit of math, and we have our answer. Let's ask if any of the others are even possible. Would it appear to go in the positive x, positive y direction? Of course not. Would it appear to go in the negative x, negative y direction? Of course not. Would it appear to go negative x and positive y that direction? Of course not. So notice, if we're just thinking logically with common sense, a lot of times we can deduce the answer without even doing much math.